Thank you.
Jorge Zubelli, who is here with us today, is the chair of mathematics at the Department of Khalifa University in Abu Dhabi in UAE. His research is concerned with the solution of relevant problems coming from applied sciences, including applications to mathematical finance, mathematical biology, and mathematical physics in general. So he has published in many relevant journals, and he also is part of several networks, scientific networks and projects that cover Europe and South America and elsewhere. So his techniques, at least in the way he describes himself, connect directly to the inverse problems areas, and he draws from analysis, statistics, and probability theory. But he also has some computational tools in his problem-solving tools. So, Jorge, I hope you can share the screen at this moment, and it's a
Yes,
pleasure to have
let
you
me
with us.
try. Thank you very much. Okay, and share a Chromium
Should be
tab.
Jorge.
Yes, let me try. I think this should work okay. Can you see it?
Yeah, we can see it. Is it okay?
Yeah, yes. Yes, from my side it's okay. Can you see my mouse? I'm not sure if you can see my mouse. It's very small.
Yes, we see it.
Yeah. It's. I wish. Yeah, I'm not going to try to change that now. But okay. So may I start? Okay. Thank you very much, Raul Temponi, Professor Raul Temponi, for this kind invitation. I've been many times to KAUST on invitations by Raul and by Peter Markovich, and I'd like to thank this opportunity. It's a pity that I'm not there with you today. I wish that was possible, but a number of things forced me to not be there. So hopefully next time I'll join you in person and go for the scuba diving and other activities, of course. So what I'm going to talk about today is the subject of local volatility models with jump diffusions and the calibration from option prices. This is actually work in the specific case of jump diffusions with Vinicius Albany, and but it's the evolution of work that I've been doing with many other people throughout the years. I'll cite the works and the names as I go along. Okay, so the basic outline for my talk is I'll try to introduce the relevance of the problem we are discussing. Then in the tradition of inverse problems, I'm going to describe the direct problem, and then the inverse problem, I'll discuss results, and then some numeric applications and some final remarks. So what is the main interest here? Well, it's coming from the fact that options and derivatives are a fundamental part of world economics. I mean, the amount of money that is exposed to derivatives is of the order of trillions of dollars in the US alone. So this is a tremendous amount of money, and certainly requires very important, very strong mathematical tools. Now, what is from the basic, what's the underlying behind this? Well, it's diffusive processes, their expected values, and control. What's the main difficulty? The main difficulty is model selection, and calibration. There is a tremendous number of different models available, and besides looking at the models, you have to be able to calibrate the models appropriately. So this is the direction we are going. And when I say here diffusive processes, I'm also now, since a few years ago, I got interested also in looking at the jump behavior. I'll describe that in a little while. Okay, So back to the history, I cannot start but without mentioning the contributions of Robert Merton and Myron Scholes, who got the 1997 Nobel Prize for their work on modeling financial derivatives, together with Black, that had passed already in 97 when the prize was awarded. And they basically introduced back in the 80s this fundamental equation called the Black-Scholes-Merton equation, which describes the price of an option. Just very brief words about that. An option is a contract that allows you to buy something or have something at a certain time, which is the expiration time that I'm denoting here by TE. And this something is dependent on time and the current underlying value of some asset X. So for example, an option, so-called call option on the Standard & Poor's index or IBM index, IBM stock value or Apple stock value is something that will give you the right to buy, let's say in 1 year from today, a certain number of shares of IBM, say, for a certain value, which is usually called the strike price. Okay, so we have then, as time goes along, and since these prices are random variables, this price of the option is also going to change with time, and so we are going to be denoting P of TX, the price of the option at time T, for spot value X, and for a payoff H as this dependent variable that we are interested on. And it turns out that P satisfies the equation that I'm describing here. I hope you are seeing with my mouse. Is my mouse at least roughly visible now? So derivative of P with respect to time plus 1/2 of sigma square in red times the diffusion term plus R, which is the interest rate, and this is always equal to 0. And here sigma, this very important quantity, is called the volatility. And this is a final value problem. In other words, a problem that we are specifying the final value, and time then runs for time less than t. Okay, so we are interested in this equation, which describes this model. Now, as it turns out, this was the first step in pricing derivatives. It was like the version 1.0 of pricing derivatives, yet it made a big impact. Now, there are many issues behind this, many approximations, many hypotheses, which I'm not going to describe in detail. The economical assumptions, the statistical assumptions, but the main one that when you look at this equation is that it's sigma, the volatility of the market, the agitation of the market is assumed to be constant. And this is definitely not the case. In fact, I'd like to show here a graph of the so-called Bovespa index. It's a very important index in South America, in Brazil in particular. So you see in red here the value of the index. So that's an average over a certain number of stocks, and people trade options based on that. And in black here, what you see is the volatility computed according to a running window that goes along with time. And it's usually a rather small window, but yet you see this tremendous stochastic behavior for the volatility as well as the stochastic behavior of the stocks. So you cannot say properly that volatility is constant, although the idea behind shows is to assume that the volatility was approximately constant, as well as the interest rate was approximately constant during the time of the life of the option, and therefore write down an equation. Well, as it turns out, as I said, volatility is not deterministic. It's even a multi-scale phenomenon, and this has been extensively studied in the work, for example, Fouque, Papanicolaou, Sircar, and many other people. It's not true that the underlying process goes along the exponential Brownian motion, which is the assumption that leads to the Black-Scholes equation, and this is even more so in high-frequency contexts. Yet, for the purpose of discussion, people talk about something called the implied volatility. It's the value of the volatility that should be used in the Black-Scholes formula, which, by the way, you can actually write explicit solutions. That equation, I didn't say that, but that equation for certain specific types of payoffs can be explicitly, you have analytic solutions. You always can also attack it with numerical solutions. But so that is the value of the volatility that should be used in the Black-Scholes formula to give the quoted price of market, or the quoted market price of derivative. Okay, so at this point, we asked ourselves what to do. Well, there are many interpretations and directions. Of course, there is econometrics interpretation, which deals with the historical volatility, and there has been tremendous amount of work on that. There is this concept of implied or implicit volatility, which is given by the market, and that somehow allows people to compare prices, because somehow prices tend to increase as volatility increases. Okay, and stochastic volatility models are also used, in particular with fast mean reversion. That led to a very beautiful work by Papanicolaou, Fouque, and collaborators. In fact, we did some work. We jumped on this bandwagon a few years ago, back in 2015, for commodities as well. Our approach is basically on the non-parametric aspect of volatility. So we are considering the volatility as some function of time and the underlying price. I'm going to discuss that more. But I should mention that I've been involved also, and many people have been involved with stochastic local volatility models. So in the present work, we are going to be focusing on local volatility and jumps. So what are the central problems? Understand the volatility behavior, protect portfolios against volatility oscillations by use of delta hedge. So by having good models, you can construct hedging portfolios, and find parsimonious and efficient models that are simple but not too simple, so that we can calibrate such models in a robust and effective way. And usually from there, one is able to price other derivatives consistently. So the work I'm considering is based on original work by Bruno Dupir, which became one of the main standards in the market, and it's called the local volatility model, and I'm going to describe it now. So here the assumption is that the volatility sigma turns out to be a function of time and a function of the underlying. By the way, if you write down a stochastic differential equation, you can motivate this model by use of a theorem by Yongi, but we're going to take this as given. So in any way, this depends the volatility on time and x is the underlying assumption, and using the same techniques that lead to the derivation of the Black-Scholes equation, you can get this equation here, which is again a diffusive equation. Again, I stress that this is a final value problem, so we are solving the equation for time less than expiration. And from now on, we are going to we're going to focus on two cases, namely the case of a so-called call, which is the one that you see here on the left-hand side, and of a put, which is the one that you see here on the right-hand side. So x minus k plus means the x minus k if x is greater than or equal to k, and 0 if x is less than k. Okay, standard notation. And the other point I wanted to make is that k here is a parameter which is the strike price. So the price here of the put, the price here of the call, which is this one on the left, means that you'll be able to buy for a value of k at the expiration a stock that's worth x. So you are in a certain sense going to do that if x is greater than k. You're not going to do it if x is less than k. Okay, if it's equal to k, it doesn't matter. So in any case, let's then focus on this equation and ask the following question. Now, suppose that I'm sitting at a certain fixed date, let's say 26th of May, 2022, and I'm looking at a derivative that's going to expire in 3 months, and a derivative that's going to expire in 6 months, and so on. So if I go, for example, to Bloomberg, or if I go, for example, to Google Finance, what I'll see is the set of prices that are quoted by the market for today with different future values, say 3 months, 6 months, 1 year, and for different strikes. So from the perspective of someone that's looking at this today, what is interesting is what's happening parametrically as a function of time and as a function of the strike. Therefore, the idea that Dupuy had was, is there an equation that is satisfied by this P as a function of those variables? And the answer is yes. And that turns out to be a beautiful result called Dupuy's equation. So if we look at U as a function of T and K and fixing little t and x, what I get is a differential equation that's very similar to the one that we just described. And suppose our reference time t is fixed, then we are considering this equation, or say t equals 0, then my capital T would be greater than or equal to 0. Otherwise, it would be time to expiration. So we are considering here the time to expiration, capital T, as our variable of interest. And so U is then given this initial value condition now. Notice that the sign here is minus, so the time is flowing now in the right direction that we are used to. And this equation turns out to be fundamental for the analysis. So now the question is, how can I, from the market prices, identify sigma? Well, so the problem statement here is, given an observed set U, we want to find sigma that best fits the market data. Note that the market data is noisy, it's sampled in different points, it suffers from discretization error, it suffers from approximations, it also suffers from bid and ask spread. So the noise is substantial, and so it's not an easy problem. Yet you want to find the sigma in the equation that best fits this model. Now there are a number of theoretical results about obtaining sigma from the market price, but we're not focusing on these theoretical results as far as PDEs are concerned. This is, of course, we're going to use PDEs, but we are going to focus on the inverse problem question here for restricted, limited data, and so on. Okay, so with that, we define this parameter to solution operator. Here, omega is going to be a bounded set on the price, something like 0 to x max, and a time that's limited also, let's say 2 years, 5 years, you name it. Okay, so in this space we are considering is h1 plus epsilon for my variance, and not volatility, for the variance, and it's taking values in L2. Okay, so the approach, the traditional approach is the traditional approach, sorry, that we took. We started this a few years ago. We took the approach of Tikhonov regularization, which is, of course, a very traditional approach in the theory of inverse problems. Is associated to the name of Tikhonov, and it plays a very important role. So we consider a convex function satisfying special properties, which I'm going to describe later. I'm not going to go into that now. We try to match our f of a, which is the parameter to solution map, with the observed u, which is u delta, which differs from the true u by a certain value, or at least distance in the L2 norm less than or equal to delta. Okay, so we are assuming that u hat is the data associated to the value that actual value a hat in the domain of f, and we are trying to find this a hat. But since we cannot find it, since the problem is imposed to introduce regularization from the statistical point of view, I'm sure that you have been discussing this throughout this conference. What you do is you use some a priori information and you impose that in this side here. Now, theoretical questions. Does there exist a minimizer to the regularized problem? And suppose that our noise level delta goes to 0. How fast does the regularized solution go to the true solution? Well, I don't have time to go into that here today, but this was done in trying to work with Adriano De Cesaro and Ottmar Scherz, published in Journal of Nonlinear Analysis 2012. So we actually discussed the convergence rates, and we proved this under, of course, some assumptions using a very broad theory developed by Ottmar Scherz and collaborators. Now, more practical questions are, can we devise an iterative algorithm to compute the solution? Does this algorithm converge? Of course, that's the natural question. Can we regularize by stopping the iteration judiciously? Well, the answer is again positive to all these questions. We have a tangential cone condition. It's a technical condition that we can prove to our problem, and that ensures the convergence of the Lenz-Weber iteration. Furthermore, we obtained Morozov type criterion to stop the iteration. This is joint work with Albany and De Cesaro. And we developed regularization by discretization with a stopping criteria. Now, we implement this algorithm with different techniques, for example, with Kalman filters, with ensemble Kalman filters. The behavior from our studies seems to be comparable. And for example, what you get in this type of example, here's an example that we did with semi-synthetic data. We took a model that's very popular in finance called the Heston model. We calibrated it to SPX model. That's a finite number of parameters model. Then from there, we computed the corresponding local volatility surface. And this was done for WTI crude oil data in the stock market. And I'm showing here in the log variables, the value of log of K over S0 and the years to maturity axis here in years. And the S, the value of the volatility is shown in this curve. Okay, so that's the type of surface that we're looking at. Okay. Okay, so now let's go to the thrust of this talk, which is the Jump-Diffusion model. So in the Jump-Diffusion model, and one has to live with jumps. I mean, with jumps happening all the time. We see, for example, the crisis of 2007, 2008. We see the flash crisis that flash. We see well, what just happened at the beginning of this year. So these jumps are part of life, and for many years, one comment that we received when we discussed this regularization approach is, but you don't take into account jumps. What happens if you have jumps? Well, the problem is by looking at semi-martingales and by writing the stock price S of t as S0. Now I'm changing notation a little bit. I apologize for that. We are using X for the underlying, but don't worry, I'll change back to X very soon. It doesn't matter. I keep changing notations. It's local notation for local volatility. So anyway, S here, the first contribution is the contribution. Yes, please. Can you hear me?
Yeah, just because your voice was coming a little bit chopped. Is it possible for you to stop your own camera? I mean, the one that shows your face. So maybe the bandwidth
okay,
will
surely, yes, indeed. Thank you very much. I'm very happy you asked that. Okay, please feel free to interrupt me also for any other questions. It's very dangerous when you're talking to yourself. So give me just a second, and I will stop my camera. Okay. Okay. Is it better now?
We hope. So continue, please, and then we'll see.
Can you hear me okay? Yeah, I hope.
Yeah.
Tell me if it's better. I can try to change to my mobile network. I'm using the
it's okay,
Wi-Fi, but I can try to change the mobile.
Okay,
good.
No, it's okay.
All right. So as I was saying, yes. So as I was saying, and by the way, my face doesn't add information to the talk. At least doesn't add too much information. So back to the equation that we're considering here, the evolution for the underlying asset. The underlying asset is following this diffusion process. Here is sigma, and because we are talking about jumps, then we have to take the limit going from the left to t prime, so t prime minus, and then you have the contribution from the jumps. So here n tilde is a compensated Poisson probability measure on 0t. I'm using totally standard notation. Of course, I cannot give all the details. This is a course in jump diffusion process by itself, but I'm using the notation following Konstantin-Tankov. Okay, and the really breakthrough that allowed us to consider this problem of calibration was a result that was proved by Anel Bentata and Ramaconte back in 2015, which is a generalized Dupier's formula. This is a very deep result, very nice result, where if you look at C now as a function of the time to expiration, which is tau, it's the capital T minus T in my previous notation, It's showing here tau, capital T minus T. And if you look at that, then C differentiate with respect to tau minus 1/2 of K square sigma square C differentiated twice with respect to K plus RK CK equals to this contribution here, which is the integral contribution due to the jump distribution. Okay, and now this turns the Pierce equation, which was a PDE, into an integral differential equation, and it includes a new term, which in principle, for proper calibration, you have to find it too. Now, one can take the approach, oh, let me try to use, let's say, econometric methods to calibrate for new, but this is not a trivial thing. And so our question here, our way of looking at this is we are going to use we are going to use option prices at different times and different for different expirations and different values of tau in order to calibrate the problem. So this is the setup for the problem. We want to find sigma from C. Okay, we do a change of variables. This is totally standard using the log prices. We consider the variance or 1/2 of the variance, and we normalize use so that at the end, what we see here is this equation, and with initial condition, and we are going to see or use as data different values of the price, of the prices in the future. Okay. The other massage that we do to this problem is following a very beautiful work of Kinderman and Meyer. We use the double exponential tail, which is a transformation based on U, so the jump intensity, and based on that, we can rewrite the operator, the integral part, as this is an equation here, integral of nu blah 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 equals the convolution of phi, this double exponential tail, with the uyy minus uy. Okay, and by the way, this is the operator that pops up also on the left-hand side as a result of multiplying by sigma. Let me just go here. You see this operator uyy minus uy popping up. This is really prevalent in the Black-Scholes story. Okay, so the domain now of the parameter to solution map. So we're going to take the same approach that I described before, and that was very successful only for diffusions. But now the parameter to solution map lives in a bigger domain. In other words, we are still working with H1 plus epsilon of a bounded domain, D, and our phi, this double-tailed jump distribution, is going to be leaving one side in W21 of minus infinity 0, the other side in W21 of 0 plus infinity. And here 2 refers to 2 derivatives in X and 1 derivative in Y. Sorry, 2 derivatives in Y in the price variable, in the log price variable, and 1 derivative with respect to time. Okay. So
can I ask
the domain, just to be precise again. Shirley, please, yes. Yes, go ahead.
Yeah, Jorge, with regards to the jump measure and the volatility function, are you making any assumptions to try to be able to identify them simultaneously? I mean, do you preclude, for example, very tiny jump amplitudes for the noise or for the jumps, or what do you do with small jumps? That's what I was trying to say.
Right, and this question is fantastic. It actually is a question by someone who knows the issue behind here. And the issue, and that's why it actually took us some time, is that whenever you discuss, so let me preface my answer with a bit of history. For a while, if you talk to the peer, for example, and people who are doing local volatility, they'd say in practice, you can always you cannot distinguish between local volatility and jumps. You can actually recreate jumps with local volatility. I think that's what you're alluding to. So we are not
at least the small
interested
jumps.
here.
Big
Yes,
jumps
exactly. Yes, right. Of course. Yes.
Them,
Yes. Sure. Of course. Yeah.
Small jumps.
And what's small, what's big? It's yeah. No. I love your question. It's a very good question. So then there were these two kind of fields that two kind of let's say teams. One Milan and I don't know. So the point is, and I agree with you. I'm not trying to prove uniqueness results here. We are enlarging our parameter space in order to provide better fit. So it's true that in that sense, we are trying to solve an easier problem, because as you enlarge the parameter set, then it might be better. But we are hoping that by using a priori information, and perhaps that's what is the best answer to your question, by using some a priori information on the a priori for the jump size distribution, which you can perhaps, and we actually did that, capture from the market distribution, from the stock price distribution or the index distribution. And by putting a priori information on the sigma, then you can try to distinguish both. But I understand that, and I agree with you, that in the limit, both, if the jump size distribution is very small, you cannot distinguish it from the local volatility. Did I kind of answer your question? Although I know that I'm escaping a little bit from it.
Yeah.
Okay.
That's exactly what I wanted to discuss.
Yeah, and I thank you very much, because that really shows what we're doing and what we are not doing. I'm not claiming that we can distinguish those. I mean, there are lots of econometric works showing that that's distinguishable at the small jump size, as you just said. Okay. So anyway, we define this domain to parameter domain of the parameter to solution map as this volatility that are perturbations of a certain predefined volatility. We can, for example, solve the problem without jumps, or we can solve the problem in a long time, kind of historical average of the volatility in the spirit of Papa Nicolau, Fuchs, and Circa. So this is so you can take A0 as you wish. Provide this in the appropriate space with W1 plus epsilon, or H1 plus epsilon, I should say. Okay, so now so we write A phi as elements of the domain of F, and the first proposition is that if we consider A phi in the domain of F and assume that phi in L1 of D is bounded by a certain constant that we call 1 over C, which depends on A bar, up bar, and lower, under bar and over bar, and R, then there exists a unique solution of this PID problem in W1 to lock. And then we use that and define a direct operator from df into the space W1 to 2, which associates from A tilde and phi u minus u of A0. And this is the solution of a PIDE with a forcing term. It's the usual trick of to Bayes theory. Properties, F is continuous, is weakly continuous. Yes, please. Yes.
Yeah, sorry for interrupting you. Just since I am the chair, count with approximately 13, 14 minutes maximum. Otherwise, it will not have questions.
Okay. Yes. Yes. Definitely. I'm planning to do that. I'm almost. Yeah. Sure. Okay. So as I said, F is continuous, is weakly continuous and compact. F is differentiable and satisfies this type of, let's say, coercivity estimate, which is very useful to prove results. And now we can attack the inverse problem. So what we do with the inverse problem? Well, that, oh, by the way, the result that I just quoted there, this proposition, implies in particular that we are dealing with a new pose problem, intrinsically you pose it, and therefore it has to be treated by regularization. Okay. So to tackle the inverse problem, we consider a surface of European co-options. We assume that it is a solution. We consider the correspondence. We consider the corresponding pair A dagger, phi dagger that solves the inverse problem. And we assume that we have observed data U delta, which is differing from U tilde less than delta, where delta is our control of the noise level. Of course, there is also statistical interpretation of that as the Gaussian distribution, appropriate space, infinite dimension space. And we apply again the Tikhonov regularization. So we consider the Tikhonov type regularization. Phi here is let's say P norm in the space of observed data, plus alpha phi x0 of x, which is a regularization functional. It doesn't need to be a norm. It could be something. It has to satisfy some hypothesis, but I specified in the paper. I don't want to go into that now. So the minimizers are called the Tikhonov minimizers or the reconstructions, and of course they depend on delta and they depend on the regularization level. And the usual question here in this game is what happens when delta goes to 0, and can you choose alpha appropriately so that you get better and better reconstructions. Now, attending to Raul's request, I'm just going to flash. I can make available these slides. They're going to be available. They are in the paper anyway. We make a certain set of assumptions which are in line with the work of chefs and collaborators. So this is part of a general theory. We have the setup for that. So we introduce the proper topologies, or spare you from that. And under those assumptions, there is a stable Tikhonov minimizer. And in addition to that, one can find a rule alpha, the regularization parameter alpha, which controls the regularization, which depends on delta in such a way that alpha satisfies the limit of alpha going to 0 and delta goes to 0, and it satisfies some asymptotic behavior of a convergence rate delta p over alpha delta. Okay. So now we're talking about penalty terms. For example, the penalty term that we consider in this particular case for the phi part is Kullback-Leibler. So we use the Kullback-Leibler divergence. And for G, for the part on the volatility, we followed the previous work we did with H1 plus epsilon norm. Okay, I'm sorry, I'm going to. And in addition, we can show that the level sets are weakly pre-compact, and therefore you can use the theory by Resmerit and Anderson and so on. Okay, so now the splitting strategy, which is the main, let's say, crux of this method, is you project your solution in the parameter space in the A part and in the phi part. A is the variance, phi is the jump side distribution or double tail distribution, and we fix one side, we minimize on that or the other, and once we minimize on the other, then we fix the A side and minimize on phi and so on. We repeat that, oscillating from one side to the other, and the point is that phi A or FA, I should say, and F phi have stable minimizers in their domain of definition. So as I said, we take phi n, the argument mean of f of a n minus 1 phi, with phi in p2 of d in the projection of the second variable. And likewise, we go now, and for that n, phi n fixed, we do a n in the argmin, and we increase n. So that's basically the algorithm. And if you start with phi, you can reverse the order of the two. Okay, so a stationary point of the functional is some point such that a hat belongs to the argmin of f phi hat, and phi hat belongs to the argmin of f of a hat. And the proposition is that for every initializing pair, any convergence subsequence produced by the splitting algorithm converges to some stable stationary point of f, or curl f. Okay, so in other words, you can do this iteration from one side to the other, and it's stable with respect to the perturbations of the data. So now, with that, we can find a criteria for stopping, and the criteria is again a Morozov type criteria, and there we can prove that there are alpha 1 and alpha 2 such that for a finite time the iterates of the splitting method satisfy these kind of inequalities. So you can use the residual to compute the stopping moment. Okay, and furthermore, every sequence of solutions obtained by the splitting algorithm satisfying the discrepance in the previous proposition, and delta goes to 0, and alpha 1 and alpha 2 are chosen accordingly as a subsequent conversion to the solution of the inverse problem. So everything matches in this by showing you some numerical and real data simulations. So we solve the PID with the Crank-Nicholson scheme. The minimization in both cases, the minimizations are done with the gradient descent, and the iteration ceases whenever we reach a certain tolerance, which is typically something like 1%. So with synthetic data, what I'm showing here is at the level of the level of the volatility, we have the predefined volatility of our simulations. It's a very simple simulation, of course, just concept, and therefore we have the calibrated and the one from the data, and you see that it's not fitting. It's not bad. It's actually fairly good, and you can confirm that by looking at the adherence of the data to the implied volatility. So in other words, we look at the implied volatility that we looked first in the beginning of our discussion, that's the result by solving in the inverse part of the Black-Scholes equation with respect to sigma. And what we get here is the matching very, very close. You cannot tell the difference. So there is a good match. This is the match on the exponential tail. This is with reconstructed with simulated data. We do see some discrepancies, some problems here. That's part of life. Yet on the left, what we have is the true line with crosses, and on the right, and the line with squares is the reconstructed. So in this left one, we are solving it very well. Okay. And on the right hand side here, what you have is the jump size distribution. Okay. Now this is the reconstruction of the local volatility, the original on the left, and after 1 and 2 steps on the right. So it converges fairly fast. Again, with synthetic data, this is what we get. And we did it also for the DAX options. And this is the, so I just showed to you the local volatility for the DAX on the left-hand side, the nice surface, and the double exponential tail, and the jump size distribution or density function. And the adherence to the implicit volatility or implied volatility is shown here. And with that, I basically like to kind of just show the final slide, final considerations, and I'll take questions. Thank you very much. Thank you.
Obrigado, Jorge.
Nada.
We have a couple of minutes for questions from the audience. We have many people interested in volatility, stochastic volatility here. So
yeah. Yeah, I'll put back the camera so that you can see my, and I can see you also perhaps. Let's see if we can. Yeah.
Go for it. Matthias.
I cannot hear. Perhaps.
Okay. Just a moment. Okay.
Yeah.
Matthias.
Thank you. Yes, thank you for your nice presentation.
Thank you.
And you have probably mentioned this already. I was just wondering, when you do the optimization, including, I mean, you have the volatility and the jump process. How then? I guess you have two Tikhonov regularization parameters. One for the volatility,
yes,
and one for
yes.
the. And how do you choose those? I mean, respectively, which one should be larger than the other, so to say?
Right. No, very good question. Excellent. First of all, let me mention that the theoretical results allow us to tell that the two parameters go to 0. Now in practical examples, what we do is, since we have tackled this problem already for the volatility part, we usually choose the parameter for the regularization from the volatility case, and then from there we adjust the parameter on the jump size part, on the double exponential tail, so that we can adjust that using the Morozov criterion. So it's kind of a splitting method too. I mean, like we are doing, in one side we solve the problem with the volatility, and then on the other side we adjust the regularization once we have the volatility. Yeah.
Yeah.
Of course, this is heuristic. It's the only thing I can say is that we have a theorem that guarantees that if the error delta goes to 0, then you have alpha 1 and alpha 2 going to 0.
No,
But
thank you
that's
very
of
much.
course that's not practical. Yeah, thank you. Thank you for your question. Very good question.
Okay, so there are no more questions from the audience. We thank you very much, George.
Thank you very much for inviting me, and really it was a pleasure. And I'm so sorry I'm not there with you. I wish I was there, joining these good, fantastic moments with you.
La próxima. La próxima.
La próxima, la próxima.
La próxima. Bom final de semana.
Thank you. Gracias.
Obrigado.
Okay. Obrigado.
Okay.
Thank you.
Thank you very much.
Thank you.
Now we switch to the laptop.
Bye.
And I do a couple